Hello everyone, my name is Wenna Song, a PhD of Wuhan University. In this video, I will talk about our study of apps auto-login function security testing via Android OS level virtualization. This talk is about a new style of customization scheme. We use this scheme to test the app auto-login function security via Android container virtualization. Here we have listed 3 questions we researched to answer. This is my outline. First, we will discuss app automatic login defects. Although the app's automatic login brings convenience to users, it has 2 flaws. First, credentials are stored locally. Second, credentials are the primary verification indicator for app automatic login. As a result, attacks can break through the login device number limit and log into the victim account stealthily. During the credential clone attack, the victim credentials are extracted to the attack's same directory. However, the traditional credential clone attack has some limitations and can be applied to the current app clone attack, such as rooted device, non-well app device consistency check, audited credential extraction. In order to solve these limitations, we propose a new data clone attack, some credential extraction method. Next, we will use OEM phone clone app to perform fraud attacks on subscription apps. Subscription apps are paid apps, and there are restrictions on the number of devices that can be logged in simultaneously. Amazon Prime Video and Netflix are examples. They include in-app purchase services. The download volume of these apps is enormous. Figure 2 shows the process of a fraudulent attack. The attacker transfers the backup data in one phone to 3 other devices. The devices accept and restore the backup data and then start an automatic login request, and the server responds to them successfully. Some well-known apps have been damaged. Fraud attacks have some advantages. As a result, the user's sensitive data will be in jeopardy without raising suspicion. We selected 29 mainstream apps to execute the attack, and 25 of them were successfully attacked. We speculate that the future case include device consistency checks. To verify this program, we expanded the test set, selected 234 different apps, and performed data clone attacks among real devices and countermeasure environments. From these 2 tables, we found some phenomena. In addition to subscription apps, we found that other apps also include device consistency checks. The number of successful clone attacks in our customized environment is higher than that between real devices. Our new experiment confirms that some apps have already performed some device consistency checks. Since we choose an Apple-level customization method, the method lacks transparency. We developed an OS-level solution named VPDroid to assist the apps across security settings. This includes 2 projects: system virtualization and customizing device properties. We include the virtualization of kernel and user space to kernel, inherit the kernel virtualization of cells, such as input and sensors, update the kernel virtualization to compatible with the new system, such as boundary and network, add additional device virtualization, for example GPS, to user space. We provide boundary sharing and device proxy so that our virtualized components are excluded from the guest, ensure the transparency of the virtualized environments. Based on the new Android OS level virtualization framework, we customize the VP device attributes, include system properties and device properties. First, when booting up the VP, we enforce the VP init process to load the customized properties from build into the VP's shared memory space. Second, other processes inquire about the customized properties at runtime by calling propagate, an API to read the data into the shared memory from other processes. Our customization functions are located at the policies where we just finish user-level device virtualization or kernel-level device virtualization. All of the customization functions work in a similar style. The first determine whether the current query request is from the VP or the host by checking the associated device namespace. For user-level customization function, if the query is from the VP, it calls propagate to acquire the customized data from the host's shared memory and then return the customized data to the VP. However, for kernel-level customization function, the customized data located into the process have no privilege to enter the kernel space. Therefore, we create a new system call to copy data from user space to kernel space. There are many advantages of VPDroid customization. In particular, we provide a wide range of device attribute customization options. In the evaluation section, we select the database about 234 apps. The experiments include performance measurements and data clone attacks. We measure runtime overhead and memory usage using two Google Nexus 6P phones. This is the result of our performance test. This is our runtime performance. This is our memory usage. To runtime overhead, VPDroid reviews performance close to native. To usage, the memory reveals that VPDroid is a lightweight system virtualization solution. We evaluate the transparency of VPDroid customization by performing a data clone attack. The last column of Table 1 shows the sources number of data clone attacks in VPDroid. We can compromise all of the 234 most popular apps accounts. The result of our VPDroid clone attack exceeds the operation between X-post and the real device. In order to prove the effect of VPDroid, we conduct comparative experiments with exciting tools. As a result, we didn't find a counterexample. This confirms that our device virtualization and customization are transparent to cloned apps. We reported our vulnerability to the manufacturer. Most vulnerabilities belong to subscription apps. Our research mainly includes three aspects. VPDroid reveals that automatic logging of app poses a severe security threat. That's all. Thank you, attention.
Hi, and here we are again after the second presentation of this very good session. So here with me it's Venna, and I'm sure I'm mispronouncing their names. I'm sorry about it. So they have just presented the paper apps auto login function security testing via Android OS level virtualization. And as before, I do invite attendees to ask questions in the chat so I can read them to the authors. I see that we already have a first question. So Xian is asking if your method works on both Dalvik virtual machine and the Android runtime.
Okay. This is interesting question. During the experiments, we have executed the test on their very DVM and ART platforms. Yes.
Okay, great.
Thank you.
So that's it's great to know that it works on both. So we know that it works both on a new Android system and even on the older ones. Um, yeah, I was wondering. I found the attack very interesting. I was wondering about the ethical aspect of when you found the vulnerability. How did you report the issue to the vendors?
Uh, uh, we respond to the manufacturer through the manufacturer's official email. This is
Okay.
one method. Uh,
Okay. And did they all reply, or someone did not reply?
and yes, some but most of them have response us, and most of the vulnerability belongs to subscription apps.
Okay. So I guess yeah, especially the ones that you were mentioning, like Netflix or
Yeah.
Amazon, are the ones who are clearly interested in fixing these issues. And how about the cases where you did not have a response? Did you still make the vulnerability public, or what did you do?
Mm, um, Let me think. I uh, can you speak? Can you repeat this question?
I can repeat, yes.
Thank you.
I was wondering, imagine that you find a vulnerability in an application that is okay, could be Netflix, and imagine that Netflix is among the vendors who did not respond to you, so did not confirm and did not fix the problem. Did you still make the vulnerability public? Did you still made the information public, or what did you do?
Yes, I made some vulnerability public. This vulnerability are uh, always showing on the CNN uh, on the some official security some official security platform. Uh, for example, CNNS. For example, CNNS. Wait a minute. Wait a minute. For example, the CNVD. This is a platform that can submit some vulnerability.
Okay.
Okay.
Okay. Um, and I was wondering if you have any evidence if this kind of attack has been performed in practice by some users before you reported it. So, do you have any evidence that these vulnerabilities have been exploited?
Uh, mm, um, the, there, in the study, we found some malware uh, made from the backup app.
Okay. So if I understand, you are aware of some malware that was using this that was exploiting this vulnerability.
Some malwares has been used the vulnerability we proposed in this paper.
Okay. Okay. And I was also wondering, I mean, your work is purely on Android, but in principle, this kind of vulnerability can affect also other systems. I can imagine, like, for instance, if I don't know, maybe browsers and so on. Did you think about exploring that direction?
Yes, even the browser, if the credentials are stored locally, and even can include some device consistency check, they can use or they can use the OEM, they can use the data clone attack and data clone type model to attack.
Okay. So is this your next paper to explore other systems?
Yes, we will study this direction. Yes.
Okay. Okay. Very interesting. I'm looking forward to hear more about these vulnerabilities. Um, One more question, unless there are some questions from the audience. I was so my understanding is that the root cause of the problem boils down to how you store the credential data locally on the device. So can you discuss a bit how to avoid these kind of problems? I mean, obviously, one way to solve it is, okay, just disable the auto login
Yes.
and basically force the user to re-authenticate every time, but it's not ideal for usability. So what are your solutions to this?
I think we can use the trust result to assist the automatic login dependent automatic login.
Okay.